the cooler part. Ladies and gentlemen, there's one variable in any environment that typically plays a critical role in virtually anything we want to study, but it's often taken for granted. Does anybody know what that's called? What that is?
Gravity.
Gravity. Gravity's everywhere. Gravity's everywhere. Gravity plays a role in virtually anything we want to study. Here's a really cool moment in and of itself. Even a germinating seed knows about gravity because when it germinates, the roots go down and the shoots go up. It's called geotropism. Your body knows about gravity in myriad ways. Every time you take a step, your bones are compressed under your own weight. And that sends a bioelectrical signal back to the body saying, keep making those bones. Those bones are really important. But say in the weightless environment of, say, the International Space Station, there appears to be no weight. There is no bone compression. And the signal back to your body is, hey, we don't need those bones. We can start excreting the skeletal system. And astronauts have to work hard with springs and straps to compress their bones to keep that signal alive to minimize bone decalcification. And you're probably all at the right age to remember when you were little kids watching the movie WALL-E. Yes? That's what this was all about. That's sort of like a central theme of the movie WALL-E. And so the point is that gravity plays a role in virtually anything we want to study. So here is the flavor of essential question that drives all microgravity experiment design. What is the role of gravity in that? What is the role of gravity in that thing over there or this thing over here? What is the role of gravity in something we want to study? That is the flavor of essential question for all microgravity experiment design. So here's the important question. If you want to understand the role of gravity in something, what needs to be the variable you change?
Gravity.
Presence of
Gravity. You need to change gravity. It's the only way to do it. And there may be a problem with that because unlike changing the temperature or the composition of the soil or the moisture content, there is no dial in any laboratory on the face of the earth where you can dial up or dial down the force of gravity. Everybody with me on that? So the problem is this. That's the problem. Now, any two masses in the universe, so let me take my 2 coffee cups, any two masses in the universe will attract each other with a force of gravity. But you don't see these coffee cups flying towards each other because gravity is an incredibly weak force. For you to actually perceive gravity in our everyday lives, at least one of the masses has to be truly massive. And then you start to get to see gravity in our everyday life. Can you give me an example of two masses where one is massive and you actually do see gravity every second of every day and you depend on it?
The sun.
So you're saying the sun and what?
And the earth.
Yeah, so it's not as immediately obvious as what I want to see. I want to see an example of a large mass and a small mass where the effect is that you depend on that every second of every day. And let me give you another hint. You're depending on it right now for you to do this Zoom video conference.
Are you going for the moon?
Well, it took the human race a long time to figure out that the moon had impact on the tides. Let me give you another hint.
The earth and
How
us.
about how about the earth and you? Right? The earth and you. In the case of the earth and you, All of the continents are pulling down on you. All of the oceans, all of the mountain ranges, the crust, the entire crust of the earth, the entire mantle of the earth, the outer core, the inner core, the piece under your feet, the mass under your feet making up the earth, and all of the mass 8,000 miles below your feet on the other side of the planet. The entire mass of planet Earth is pulling down on you with a force of gravity. And we call the force of gravity exerted by Earth on you your
Mass?
weight.
Yeah.
Yes. The force of gravity exerted by all of planet Earth on you is your weight. It's what you see when you stand on a bathroom scale. It must be a weak force because it took the mass of the entire sphere of Earth pulling down on you for you to see a force of, say, 150 pounds. Okay, so now here's my next question. What do you think intuitively happens to the force of gravity between two masses when I move them farther away from each other?
Dissipates.
They weaken.
They weaken, yeah, that's right. It's kind of intuitive because the farther away they are, the less they know of each other. So the force of gravity weakens. So if you want to do a microgravity experiment, okay, if you want to test the role of gravity in something and you have to change the gravity variable, can somebody give me an approach to such an experiment?
Move away from what you're testing from.
Well, the gravity that is everywhere that we take for granted is the force of gravity exerted by planet Earth on a plant or a bacterium or a seed or us, right? It's the force of gravity exerted by planet Earth on whatever we're studying. That means its weight, right? It's the weight on that object. And so rephrase that, Justin. What would be the way to do this? Say what you said before.
Move away from the object that you're.
And what's the object in question?
The Earth.
The Earth. So one way to do it is to move your experiment into space away from the Earth, and you have done the experiment in a lower gravity. Okay, so from the experiment's vantage point, it's operating in a lower gravity. What other kind of experiment do you need at the same time?
A control experiment.
A control. And what would you propose as the control experiment?
The same experiment, but conducted on Earth.
So the idea is that if you conduct the same experiment at the same time on the surface of the Earth, and you have this experiment going far from the Earth in a lower gravity, when you bring the flight experiment back and you put them side by side, this one operated in a lower gravity, this one operated in Earth gravity, and you can look for behavioral differences in the two experiments to reveal the role of gravity. Does everybody understand that?
Yes.
Okay, so a microgravity experiment's a really simple experiment. You have to change the gravity variable. That's all it means. And one way to do it is to take the experiment far from the Earth, and therefore the gravity is lower, have a control experiment on the ground in gravity, and when you bring the flight experiment back, maybe you need to deactivate the flight experiment before you bring it back to Earth gravity. But when you bring the flight experiment back and you put them side by side, this one operated in lower gravity, this one operated in Earth gravity as the control, and you look for behavioral differences in what you're studying to reveal the role of gravity in that. So everybody got that? Okay, so now, does everybody understand the basics of what a microgravity experiment is? Everybody's good, okay. I still haven't told you why the word microgravity is being used, because that's the scary term, but I'm going to get to that now. Let's understand this a little bit deeper, okay? What is the tallest mountain on Earth?
Everest.
Mount Everest. Not tall enough. I need to find me a mountain that is 47 times higher than Mount Everest. 47 times higher than Mount Everest. What's really cool about my mountain, I'll call it Jeff's Peak, okay? What's really cool about Jeff's Peak is when you go to the top of this mountain, 47 times higher than Mount Everest, you are now 250 miles above the surface of the Earth. Can anybody tell me what object I might find 250 miles above the surface of the Earth?
The International
Mauna Kea.
Space Station.
Volcano.
The International Space Station. So when I go to the top of my mountain, I'm at the same altitude above the surface of the Earth as the astronauts in the International Space Station. In fact, my mountain is placed just right so that the International Space Station flies right by my face. And I look through the big cupola, the big window, and I see the astronauts inside. Now, you've all seen videos of astronauts in space. Can you kind of characterize what their environment looks like? I mean, what are they doing? What are they experiencing?
Floating.
Floaty.
They're floating around. There's no up or down. It's as if what's missing?
Gravity.
It's as if there's no gravity. And if there's no gravity, there's no weight, which means we can call the environment weightless. Does everybody get that, right? If there's no gravity, there's no force of gravity on them, there's no weight. They don't have a weight. They are weightless and they're floating around. And so, wow, that's pretty cool, because if I take my experiment there, there's no gravity in space. That's way cool. Okay, now here's the deal. I'm on my mountain and I'm seeing a therapist for this. I'm really sorry. I have to make a confession. I seem to have to take my bathroom scale wherever I go. I don't know. So I happen to take my bathroom scale to the top of Jeff's Peak, and I put it down on top of the mountain. And the International Space Station astronauts are flying right by my face, and I look through the big window, and they're floating around as if there's no gravity whatsoever. And I'm at the same distance from the surface of the Earth as they are, and I stand on my bathroom scale, and what do I weigh?
0.
Okay, that's a good answer, because I'm at the same distance from the Earth as they are. So if they're weightless, if they're not seeing any weight, I must be weightless too. Does anybody have any other answers?
You'd be a small amount more because you're on the mountain, and that'd be having a pull on you.
So you think that it's a small amount because I'm on the mountain pulling on me?
Yeah.
Okay, that's a good answer. Anybody else?
Maybe because you can stand on the scale, you're up there, has to be some sort.
The astronauts are currently falling, always falling, so they're weightless because they're falling around the Earth.
Is this making you all think?
The astronauts are falling as they circle and orbit the Earth, so they're weightless because they're falling. But on
You're
your
still your same weight. However, gravity is affecting that. It hasn't changed your weight.
Okay, so all of the things that you're saying, they're logical, they're rational, but what I want to do is thread through logic to get to an understanding. Okay, so that's what I'm going to do now. I'm going to kind of pull all of your comments together. Turns out that when I step on my bathroom scale, I weigh almost the same as what I weigh on the surface of the Earth in my bathroom at home. I weigh 90% of my surface weight, which means that something's weird is going on. So what is the diameter of the Earth? Let's use miles because it's a familiar unit. I know we're supposed to be using the MKS system, but bridging to the familiar is a much more conceptually powerful way to learn. So what's the diameter of the Earth? 8,000 miles. How far above the Earth's surface is the top of my mountain or the astronauts, because we're both at the same location? 250 miles, right? So here's a sphere 8,000 miles across, and I am standing on my mountain 250 miles above the surface of the Earth, which is where the International Space Station is. So is the top of my mountain out here? Where is it?
Pretty close. More closer.
Tell me when to stop.
Like there.
About there.
It's like right here. It's skimming the surface of the Earth just above the atmosphere. And just as a climate change, oh wow, okay. The atmosphere compared to the Earth is thinner than the skin of an apple compared to an apple. That's how fragile the atmosphere is. And so the astronauts and me on top of my mountain are really, really close to the Earth. So have we gone far from the Earth?
No.
No.
So what can you say? What can you say about the force of gravity exerted by Earth on me?
Wrong.
The same.
It's almost the same as on the surface of the Earth because I haven't moved very far from the Earth. That's why I weigh 90% of what I weigh on the surface of the Earth. But the astronauts, now here, kind of follow this, okay, this is really important. The astronauts are the same distance from the Earth as me on top of my mountain. So the force of gravity exerted by the Earth on them, their weight, is also 90% of what they weigh on the surface of the Earth. They are not weightless. They are weighted because the force of gravity exerted by Earth on them or anything is called its weight. And they're almost at the same height above the surface of the Earth as the surface of the Earth itself. So does everybody understand what I just said? The astronauts have a force of gravity exerted on them that's almost the same as on the surface of the Earth. It's 90%. Why is it 90%?
Because you moved away from the Earth, you're not.
Because they
like,
moved a
directly
little
on it.
bit away from the Earth, okay? So can somebody tell me conceptually what the disconnect is? What's the disconnect?
Astronauts are falling.
Okay, so now we're getting to that part, okay? So the disconnect, let me tell you what is behind the conclusion that I just heard. What I asked is what's the disconnect? And the answer is if I'm at the same location above the surface of the Earth as the astronauts, why am I standing on a scale and weighing almost the same as what I weigh on the surface of the Earth, yet they're floating around as if there's no gravity at all? That is a problem. And most human beings on the face of this planet think that the astronauts are weightless because they're in outer space. Like gravity somehow magically disappears in outer space, and that cannot be. So to understand this, I'm going to take you to the top of the Empire State Building, my favorite building. And what I'm going to do is I'm going to go from the ground floor to the 104th floor where the observation deck is. And by the way, ladies and gentlemen, is the Empire State Building a big thing? Is it big? How does it compare to Mount Everest?
Small.
How does it compare to a mountain 47 times higher than Mount Everest?
Small.
It's
Relatively small.
insignificantly
Nothing.
small. It's insignificantly small. So if I go to the 104th floor of the Empire State Building, am I still on the surface of the Earth?
Yes.
Yeah. Okay. So here's the deal. I told you I'm strange. I bring my bathroom scale everywhere I go. So I get into the elevator. I go to the 104th floor, and inside the elevator is my bathroom scale. And by the way, before I went to New York, I went to a local pre-kindergarten classroom, and I grabbed one of those chairs. And what's cool about that chair is when I stand on it, I'm 1 foot above the floor. I'm 1 foot above the floor. And by the way, and let this sink in, the elevator has no windows. Okay, so now I go to the 104th floor. The doors open up, the elevator's stationary. It's like the elevator's part of the 104th floor. I see people walking around when I turn my back to the door because my back is to the door. I said, oh, look, there are people walking around. And I want to do my experiment. So I step on the chair. I walk down, I step down 1 foot onto the bathroom scale. And what do I weigh?
Your normal
Half.
weight.
My normal weight on the surface of the Earth, because you're not going to see the difference on a bathroom scale when I go up 104 stories. Okay, everybody with me on that? Give me a thumbs up. Okay, now science is about reproducibility. So I'm going to do the experiment over again. So I get up on my chair, a foot above the floor. The bathroom scale's on the floor below me. I'm going to step on the bathroom scale just like I did before. And the moment I'm walking off the chair, the instant I'm walking off the chair, the doors of the elevator close and something bad happens. Somebody cuts the cable holding the elevator. What happens?
You are now weightless.
Falling
Okay.
down.
Okay, so I go down, I start falling. What's happening to my speed?
It's
Increasing.
increasing.
It's increasing. What do we call an increasing speed? It's
Acceleration.
accelerating. What is causing the acceleration?
Gravity.
The force of gravity exerted by Earth on the elevator, the bathroom scale, the chair, and me. What do we call the force of gravity exerted by Earth on the elevator itself?
Free fall.
Drag.
Okay, let's try it again. What is the force of gravity exerted by all of the planet Earth on the elevator?
9.8 meters second square.
It's the elevator's weight, right? The force of gravity exerted on anything by planet Earth is the object's weight, right? So the force of gravity exerted by Earth, I know it was a dumb moment. The force of gravity exerted by Earth on the elevator is the elevator's weight, so it is falling under its own weight. That's where that expression comes from. Ooh, there's an oh wow moment right there. Now, it keeps accelerating. Can somebody tell me what the acceleration due to gravity is?
9.8
9.8 what?
meters per second squared.
9.8 meters per second squared. It's a number we all memorize. We say, oh, hey, I know the answer to that. It's 9.8 meters per second squared. For those of you who just said 9.8 meters per second squared, what does that mean?
Fast.
What?
That you're going to accelerate by 9.8 meters per second in 1 second.
Okay, if you're not going to accelerate, so let me just kind of change it a little bit. You're very close. Your speed will
Yeah, your speed is going to
increase.
change.
Yes.
Exactly. It's going to increase by 9.8 meters per second in 1 second.
Yeah, so every second your speed's going to increase 9.8 meters per second. And you know what? I still don't know what that means because I don't work in meters in my head. It's not a bridge to the familiar. It's just a number to memorize. And if you're just asking students to memorize stuff, no learning is taking place. They need to have a conceptual, emotional response to what you're teaching them, which means you have to build bridges to the familiar. And the familiar in this case is a recognition that all of you drive cars or take public transportation, and you know what it means in terms of miles per hour. That's a familiar bridge to the familiar. So the acceleration due to gravity in that unit is every second your speed increases 20 miles an hour. Every second your speed increases 20 miles an hour. So after 1 second, how fast are you moving?
Miles an hour.
20 miles
20
per
miles
hour.
an hour.
20 miles an hour. After 1 second, your speed increases 20 miles an hour. You start from rest. After 1 second, you're moving 20 miles an hour. After 10 seconds, how fast are you moving?
200 miles.
200.
200 miles an hour. If it's a big enough shaft in the elevator and you don't go splat, after 100 seconds, how fast are you moving?
2,000.
2,000.
2,000 miles an hour. The acceleration due to gravity is huge. But what fills the shaft of the elevator?
Air.
Air.
Air. And what will air do?
Slow you down. Air resistance.
It'll slow you down because of air resistance and or drag, another way to say it. And to give you an example of this, if I parachute, I jump out of a plane, for the first few seconds, I'm accelerating at 20 miles an hour, increase in speed every second. But the speed, the drag force due to the air goes is dependent on the speed. So as my speed increases, the drag force increases until finally I can't go any faster because of the air resistance. What do we call that?
Terminal velocity.
Terminal velocity. And for a human being, it's about 100 miles an hour, which is pretty fast, which means that you're not going to survive to parachute another day. You're going to go splat on the ground at 100 miles an hour impact. So what you do is something smart. You deploy a parachute, which increases the drag dramatically to slow you down even more so you can parachute another day. Everybody got that?
Yes.
Give me a thumbs up. Cool. So what we're going to do, ladies and gentlemen, is we're going to suck all the air out of the elevator shaft. And as the elevator car goes down in the shaft, we're going to make sure there's no friction between the car and the shaft, right? So if we take the air out, so there's no air resistance and there's no friction between the sidewalls, what is the only force acting on the elevator?
Gravity.
Gravity. And what kind of special falling happens when the only force acting on a falling object is gravity?
Free fall?
Free fall. It is free of all other forces. And if that's the case, until you go splat, okay, will you keep accelerating?
Yes.
Yes, you'll keep accelerating. Now, here's the next piece of this. The elevator, me, the bathroom scale, and the chair are all accelerating down. Are we accelerating down together at the same acceleration?
Yes.
No.
Okay, you might say yes, you might say no. So here's how many people say yes, give me a thumbs up. How many people say no, give me a thumbs down. How many people say, I really don't know? Okay, so let's see, Avery, if we can help you out. I've been working out before this Zoom video conference. I'm a big guy, and in one hand I hold a Toyota Camry. Okay. I know that's kind of a weird picture, but yes, okay. I'm holding a Toyota Camry in one hand, and I'm holding a bowling ball in the other hand. If I drop them from the same height at the same time in an airless environment, so they're in free fall, if I drop a Toyota Camry and a bowling ball from the same height at the same time, will they hit the ground at the same time?
Yes.
Okay. Well, you might not agree with that, right? The answer is yes, but let me drill a little bit deeper. Is the Toyota Camry the equivalent mass of a certain number of bowling balls?
Yes.
Can I think of the mass of the Toyota Camry as a bunch of bowling ball masses? Yes, no?
Yeah.
Yes.
Yeah. So let's say the Toyota Camry, when I measure its mass, it's the equivalent of 456 bowling balls. So instead of dropping the Toyota Camry, I'm going to drop the same mass as 456 identical bowling balls, which, by the way, is identical to this bowling ball over here. So now I'm going to drop 457 identical bowling balls from the same height at the same time in an airless environment. Will all these identical bowling balls hit the ground at the same time?
Yes.
Yes.
I think Avery is saying yes.
Yes.
Which means that the acceleration due to gravity has nothing to do with the mass you're dropping. Okay? And that's why when you ask what the acceleration due to gravity is, and somebody says 9.8 meters per second squared, it's not, there's no caveat on it depends on mass. It doesn't depend on mass at all. So is everybody with me on that?
Yes.
Okay, so here's the deal. I get into the elevator, I'm doing the same experiment all over again. I get up on the chair, a foot above the floor. The moment that the doors close behind me, I don't see that happening. It's behind me. The doors close behind me. And the moment I'm walking off the chair, somebody cuts the cable holding the elevator. There's no air in the shaft. There's no friction on the sidewalls. You said that the elevator is in free fall. But is it true that the elevator car, Jeff, the bathroom scale, and the chair are all accelerating down together because the acceleration due to gravity has nothing to do with mass?
Yes.
True.
Yes? Everybody says yes. Okay, good. So here's the deal. Let's say Jeff moves down 100 feet in 10 seconds. Is it true that the elevator's floor will also move down 100 feet in the same 10 seconds?
True.
Yes.
Let me say it again. I'm standing on the edge of I'm not standing on the edge of the chair anymore. I've just, that moment, walked off the edge of the chair. I'm a foot above the floor. And if I go down due to free fall 100 feet in 10 seconds, will the floor move down 100 feet also in 10 seconds?
Yes.
Yeah.
So if in the elevator I move down 100 feet towards the floor, is it true that the floor is going to move down away from me 100 feet in the same amount of time?
Yeah.
Yes.
Can I catch the floor?
No.
No.
I can't
get to the
catch
bottom.
the floor. Every time I go towards, since everything is accelerating down together, every time I move towards the floor a certain distance, it moves away from me a certain distance. So in my elevator, what do I see?
You're floating.
I'm floating a foot above the floor. Do I see the floors of the Empire State Building rushing by me at an ever increasing speed?
There are no windows.
There are no windows in the elevator. Barry Manilow is still playing on the sound system. It must be Bluetoothed in. Okay, so here's what I did. Okay, I did the first experiment. The elevator is stationary. I step down on the scale. I weigh almost the same as what I weigh on the surface of the Earth. I want to do the experiment over again, so I do it exactly the same way in the same elevator. I step on the chair, and the moment I am walking off the chair, unbeknownst to me, somebody cuts the cable on the elevator. There's no air in the shaft. There's no friction. I'm in free fall. And soon as I walk off the chair, I'm floating. And I look around this elevator. It looks exactly the same. I did the experiment exactly the same way, according to me. And somebody turned gravity off. There's no gravity in my elevator. I'm weightless. I'm floating. And the irony in this story is that it's the force of gravity exerted by Earth on the elevator, the bathroom scale, the chair, and me that are causing us to plummet at an ever-increasing speed. But inside a freely falling laboratory, everything will behave as if gravity is turned completely off. It's called the Einstein equivalence principle. Does everybody understand what I just said here? That's like way cool, right? And so now you didn't know that I was an alien. And the reason I say that is actually I've been talking to you with no air in this room. There's no air in this room. I've just been sending my thoughts to you, and my mouth is moving, but there's no air in this room. And so if there's no air in this room, if I drop this ping pong ball, is it in free fall?
Yes.
Yeah, this is the elevator. Look. Now, a force is a push or a pull. The force of gravity is pulling down towards the other mass, right? So that's a pull. But I can also push something. I can take this ball and I can push it with my hand. I can give it a little force. And when it comes off my fingers, it's going to come off with a certain speed. So once it leaves my fingers, it's coming off with a certain speed. But once it leaves my fingers, if there's no air in this room, what's the only force acting it when it leaves my fingers?
Gravity.
Inertia.
Gravity. So when I do this, is it in free fall?
Yes.
Let me say it again. I can push it and give it a little speed. I can accelerate it from 0 to a certain speed by pushing it. But once it leaves my fingers, the only force acting on it, if there's no air in this room, is gravity. It is in
Free fall.
Free fall.
free fall. So somebody provide an understanding. Describe the path that it'll take when it leaves my fingers.
Parabolic path.
A parabolic path, so it'll arc and hit the Earth. What happens if I throw it a little faster?
It will miss the air.
It will. Oh, you're getting good. Okay, you're almost there. If I throw it a little faster, it'll make a bigger arc and hit the Earth farther away. If I keep throwing it faster and faster, it makes a bigger arc and it hits farther away, until finally, if I throw it really, really, really fast, the arc it makes is so big, it will swallow all of planet Earth. And in the opposite direction, I can catch it in 90 minutes. If there's no atmosphere on Earth, right? If there's no atmosphere on Earth, if I throw it really, really fast, it will make such a big arc that it will swallow all of the Earth, and I can catch it in my hand in 90 minutes. This is the elevator. This is the International Space Station. The International Space Station is in free fall. It is freely falling around the Earth, and the force that's causing it is the force of gravity towards the center of the Earth. Just like if you take a string and a bucket with water and you're going like this, right? You're making it go around in a circle, and the force is coming in towards your hand along the string. So the International Space Station is a continuously freely falling laboratory. The force of gravity exerted by the Earth on the astronauts is is 90% of their normal weight, so they're weighted. But in a freely falling laboratory, it appears as if gravity's turned completely off. And the force of gravity exerted by Earth on the space station and the astronauts are causing them to go around in a circle around the Earth and not flying off into deep space. Does everybody understand what we just experienced?
Yes.
So in summary, what I said is if you could change gravity, a microgravity experiment is really simple. You bring one experiment to a place where gravity is different. You have a ground control experiment. You bring them down. You compare them side by side. According to the experiment, you've changed the gravity variable. Great. It looks like there's no gravity on the International Space Station. So let's just bring the flight experiment there, have a ground control. That's a microgravity experiment. Perfect. But I wanted you to have a deeper understanding of that. And what I wanted to show you is that the force of gravity exerted by the Earth on anything is called its weight. The force of gravity diminishes when the two masses are pulled farther apart. But the International Space Station is so close to the surface of the Earth that they've not moved very far away from the surface of the Earth. So the force of gravity on them, their weight is almost the same as in their bathrooms at home on the bathroom scale. And then I took you into the elevator and I showed you, wow, in a freely falling laboratory, everything behaves as if gravity's turned completely off. And then I showed you that the International Space Station is the elevator. It just was given and imparted an initial speed of 18,000 miles an hour. And what does that job? What gives the International Space Station a speed of 18,000 miles an hour?
A rocket.
Rockets. Okay? And so does everybody understand the basic physics behind what we're talking about here? Give me a let me see in UCF and University of Central Florida, give me a thumbs up in the air if you understand this. Okay, cool. So now that finishes the idea of microgravity experiment design. But I have to ask this question. How many of you feel comfortable about what a microgravity experiment is? And let me tell you one last thing to put the last puzzle piece in the puzzle. The term microgravity means weightless. It means weightless. A microgravity experiment is an experiment conducted in a weightless environment. That's all it is. So we're good? Any questions?